Hello, in this video, let's work on one example where we need to use ratio test to identify the convergence of the series. In this example, we're working with a series from 1 to infinity of 9 to n all over n plus 1 times 5 to the 2n plus 1. I usually recommend to start with a divergence test because why would you want to work very hard for the ratio test, divergence test, if the divergence test might just show you that the tails do not go to 0, or basically the limit at infinity is not 0, and if it's not 0, then you right away can conclude that the series diverges. Then we check the limit at infinity, and as you can see, it's not very straightforward. You have two exponential functions, one at the numerator and the other one in the denominator. They have a different basis, and also denominator is multiplied by the linear n plus 1. It's not very clear which one is faster, or maybe they have the same speed, so we will probably put a question mark on that. We don't know which one is faster. The top is faster, then everything is infinity. The bottom is faster, then everything is 0, or maybe something different. Then this is the case when divergence test does not help at all. So we're actually going to proceed with the ratio test. The ratio test, RT, basically tells us to check the limit. We're going to call it L. L is a limit n goes to infinity of the next term, an plus 1, over an, ignore negative signs if there are any. And we're going to build this ratio, and that's why it's called a ratio test, slowly, and then simplify everything and see how it goes. So an plus 1 term, that's your next term. So I'm looking, I can even look at this piece here, because that's my an. And I will substitute everywhere I see n plus 1. That makes sense. And you have to do it carefully, saving all the operations and parentheses. So we have an, we have 9 to the n. Now we're going to have 9 to the n plus 1. We had n plus 1. Now we're going to have n plus 1 parentheses. You see, I'm color coding it for you. Plus 1. We also had, and that's the most confusing part for students, so pay attention here, 5 raised to 2n, but now we're going to have n plus 1, and parentheses here are extremely important. If you don't have good habit to put parentheses, then you will not do this problem right. So that's very crucial to make sure you understand that these parentheses over here changes the whole result. And that was my only an plus 1. Now I will divide by the an, that's what the formula says, but it's just smarter to multiply by the reciprocal of the original fraction. So I'll multiply by the original an, but flipped. And the fancy word for flipping means multiply by the reciprocal. So I will have n plus 1 and 5 raised to the 2n plus 1 at the top, 9 to the n at the bottom, and an absolute value to ignore any possible negative signs. Now I have to work with this, and I have to simplify it somehow. Let's see how we can work with expressions like this. And it's still a limit, remember that. And that's going to be a huge fraction. So the idea here is to collect terms that looks the same, close to each other. Then it will be easier. And I will color code everything for you again. 9 and 9 definitely should be collected one on top of each other. 9 raised to the n plus 1 over 9 to the n. Done. Now, n plus 1 plus 1 and n plus 1, let's collect that. N plus 1 at the top. What is n plus 1 plus 1? That's n plus 2 at the bottom. Collect it together. And now finally the hardest part is to simplify the 5 to the exponent parts. The top one does not have to be simplified, so it's just 5 raised to 2n plus 1. And the one at the bottom, let's simplify. It's going to be 5 raised to the, I will take a pencil, and over here we'll make some small calculations. It's going to be 2n plus 2 plus 1. Make sense? We're distributing 2. That's what I just did. Distributed 2. 2n plus 2 plus 1. What is that if I'm calculating? It's going to be 2n plus 2 plus 1. That's plus 3. And now I have all of those parts. Do we need absolute value right now, by the way? 9s are positive, n plus 1, n plus 2 are positive at infinity, right? then 5 to something is positive. So I don't need absolute value anymore. None of these factors are negative. Now it's time to simplify. Let's see what's gonna happen. I will keep color coding everything for you so you can have good notes. In green color, I have 9. 9 to the n plus 1 over 9 to the n gives me just 9 at the top. Because remember, it's a property n plus 1 minus n, right? So n minus n is 0 and only 1 stays. Review the video about the properties of exponents. Do not touch n plus 1 and n plus 2. These do not simplify. Remember that. They do not simplify like this. Many students do this mistake. Since you have addition or subtraction, you cannot do that. 5 will be simplified. Let's do that carefully. Same rule. 5, it will be 5, 2n plus 1 minus 2n and minus 3. Does that make sense? Because I take and subtract whatever exponent is at the denominator over here. That's 2n minus 2n, that's 0, and 1 minus 3 is negative 2, so actually this 5 will be in the denominator. But since n cancelled out, it will not anymore do any difference for the limit. So let's finally quit writing the limit and write down the answer. What is the answer? Since I have a leader at the numerator, I guess let me rewrite it for you to see the final beautiful limit. The final beautiful limit is 9 times the constant 5 raised to the 1 minus 3, that's just minus 2, times n plus 1. Is it n plus 1 on the top? N plus 1. N plus, yeah, looks good to me. Looks good to me. N plus 1 over n plus 2. Finally, the limit will only now show up from this piece, n plus 1 over n plus 2. And we know how to do it. Both n and n has the same exponent, so the answer will be the ratio of the leading coefficients at infinity. And that is 9 over 5 squared. 9 over 5 squared is 9 over 25. And that is actually not important that it's 9 over 25. It's going to be the same answer if it's 9 over 17 or 0.5 and so on. What is important, do you guys remember? It's important it's less or greater or equal to 1. If it's less than 1, the conclusion follows answer. Since a limit of the ratio test is less than 1, then by the theorem, the series converges. How? Absolutely. Absolutely. That means series of absolute value converges as well, absolutely. And that is the answer. Good job for watching. Practice more limits and you will be very fast at this. See you next time.